What's up everyone? In this video we'll see how to use the polarization optics to read the displacement using the interferometer assembly and use the amplifier to drive this air bearing stage, which will be feedback controlled using the built-in line scale with the stage. Then we'll read the motion of the stage using the interferometer. You've been provided 6 pieces of polarization optics. There are 2 quarter wave plates, 2 circular polarizers, and 2 linear polarizers. In our assembly, we'll be using 2 quarter wave plates and 2 circular polarizers. The linear polarizers are really for you to play around with it. The quarter wave plates are mounted in a chrome plated steel washer with a magnet in between. And the circular polarizers are mounted in zinc plated steel washer with a magnet. Both quarter wave plate and circular polarizer has 6 mm aperture. The linear polarizer has only 3 mm aperture. Let's see how to distinguish these 3 polarization optics. We have, as you know, the linear polarizer reflecting from the mirror. And I'm going to put a quarter wave plate in front of the laser and try to rotate it. As I rotate, you can see the intensity of the laser is not changing at all. From the other side, this is a quarter wave plate. The next one is a circular polarizer. Circular polarizer is nothing but one side it's made of a quarter wave plate and the other side is made of a linear polarizer. And this one is in 45 degree with respect to the quarter wave plate. If I put the quarter wave plate side where the laser is going through it, you can see the intensity is almost about the same when I rotate it. When I change the side, when it goes to the polarizer side, you can see the laser almost getting attenuating. So that's a circular polarizer. On the linear polarizer, you will see the attenuation on both sides, of course. This is one side. This is the other side. I went ahead and put a quarter wave plate on this corner cube. So the laser comes out, reflects from the mirror. This laser is linearly polarized 45 degree with respect to this polarized beam splitter. One beam goes through, which I blocked here, and the other beam reflects off the splitter and goes to the corner cube. This side, let's say it's S polarized, and let's say this side is P polarized. As the S polarized light goes into the quarter wave plate, it's going to convert into a circular polarized light, reflects from the corner cube. As it comes back, it's going to come out as P polarized light, and so that it can go through the beam splitter. One thing to notice, you can see this corner cube is placed at an angle. That's because to avoid back reflection from going back to the laser. So the front surface of the corner cube, the 4% reflection of it is gonna go away in this angle, but the actual reflection from the back of the corner of the cube is gonna come through and goes there. So if you see the intensity here, it's not that intense because the light coming back from the corner cube is still S polarized. So most of the light will get reflect back. So for us to make it into a P polarized beam, let's put this corner cube on it. Sorry, the quarter wave plate on it. And rotate it to maximize the intensity coming out of the corner cube, going through the polarized beam splitter. Let's do the same for the other side. Now the beams are interfering on top of each other. I went ahead and mounted the 50-50 beam splitter and the photodetectors. The detector PCB boards are mounted in a way that both the cables come from the same side, so that you don't interfere with the beam that's going on around here. The photodetector is connected to the PCB, which is connected to the MyRio. Let's go and mount this. As you lower this detector bench, it should be in a way that the beams are aligned to the holes on this photodetector mount so that the beams can reach. I think I got the Z height okay there. Let's go ahead and adjust the lateral alignment. Now the beams are going through the photodetectors. Let's go ahead and put the circular polarizer on the 50-50 beam splitter. Note that the beam should enter through the quarter wave plate side and the photodetector should face the polarizer side. All right, that looks good. I went ahead and opened the LabVIEW project file. Let's open this real-time LisaView fit program. This program plots the two photodetector signals. Let me go and run it. Right now, since the photodetectors are saturated by the laser, we are reading the maximum voltage here. The photodetectors that I'm using has a larger gain, so I have this problem. The ones you guys use may not have this problem. So I'm going to go ahead and slightly misalign the photodetectors to solve the saturation. I'm going to lower the detector bench so that the detectors don't get saturated. As you can see on the screen, the photodetector 1 is not saturated that much. Let's leave it at around 3 volts peak. The photodetector 2 is still saturated. I'm gonna come down and loosen this screw that misalign the detector. I'd say that's pretty good. As you can see on the PD1 versus PD2 plots, you're already getting a LisaView. We can rotate the circular polarizer so that the ellipse can be made as close to a circle. As you can see, as you rotate one versus the other, becomes circular, elliptical, etc. Since I'm touching things, things are already moving. That's what's giving you the LisaView. I would continue to touch the top of the corner cube. And then if I come and stop the program, the data was collected by this ellipse fit function thing going on here. Then you'll get the fit parameters. So far, I've been, touching on top of this corner cube to get the LisaView, and we were plotting it on the LabVIEW screen. One thing we need to make sure is the shape of the LisaView stays almost the same for the full travel of the stage. You can see on the LabVIEW screen it changes a little bit as I move from one extreme to the other extreme. So this change is mainly due to the stage travel axis not being exactly in line with the laser beam axis, and also possibly due to the angle at which the beam enters and leaves the quarter wave plate. So this variation in the LisaView shape will show up as a non-linearity in your interferometer measurements. So you have to play with the alignment to get it to stay as same as possible. Before we turn the amplifier on for the stage actuation, let's open this program up. Have the power supply on already. So run this program. This program spits out 0 volts that's going into the DAC that sends the voltage signal to the amplifier which controls the stage. We want this to be sending out 0 when we flick the switch on or off anytime you flick the switch. Now the amplifier is on. Let's turn this program off. Let's open this next program. What this program will do is move the stage back and forth to find the limits. When it does that, you will see this indicator go left and right. And once it finds the limit, the integral controller that or the PID controller that I've used will settle the stage to its mid-travel. Once it does that, we can run a ramp function. So the stage motion will be controlled to this ramp input with the feedback control from the line scale that's built on the stage. And this plot here will show the displacement monitored by the interferometer using the fit parameters from the program we ran earlier. So the fit parameters goes in here, and the phase gets unwrapped and converted into displacement values. Let's go ahead and run the program. Here you can see the stage moves back and forth, finds the other limit. Now it's going to settle to its mid-travel. You can see the PID controller doing its job. Remember, it's using the line scale feedback. That's auto scale so that we can see the interferometer values. So let's turn the ramp function on. This is a pretty lousy PID gains, but does the job of demonstrating things. So you can see the ramp is going 2 millimeters peak to valley. So you can see the interferometer values going from, let's say, 700 micrometers to 2700 micrometers. It's very critical to keep the loop speed fast enough and they don't finish late, so that you can keep track of the interferometer displacement values. Thank you.